So next we are going into the photosynthetic response curves. So photosynthetic response curves is nothing but curves that represent how photosynthesis vary with various environmental factors. And some of the main environmental factors always generally analyzed are the how photosynthesis vary with varying light intensity. What is photosynthesis response when the intercellular carbon dioxide concentration changes, and how does photosynthesis vary with varying temperature. So the three most commonly used photosynthetic response curves are called ACI, AQ and AT curves. So ACI curves are called carbon dioxide response curve because they are the plots of net photosynthesis against intercellular carbon dioxide concentration. So in these plots, you can find that in the y-axis, you will see net assimilation or net photosynthetic rate, and in the y-axis, you will find varying intercellular carbon dioxide concentration. That is, what is the concentration of carbon dioxide inside the leaf. Now, if you go more into the details of this ACI curve, we see that in this plot itself, we see that the curves are not partitioned, but there are certain faces for the curve. For very low values of or a value up to around 600 or 500, we find that this curve is dominated by the Rubisco limited photosynthetic phase. We had studied in the FvCB equation about a photosynthetic rate called Rubisco limited photosynthetic rate. So if you see here in this curve, we see that the minimum and FvCB equation says that the minimum of Rubisco RUBP regeneration limited and TPU limited are considered as the net photosynthetic rate. So here if you see the curve, if you see here, there are three types of curves. One is the straight line that is depicting the triose phosphate utilization rate. One is the one with the dashed lines. The dashed line is depicting the RUBP regeneration limited phase, and this dash dot dash line is representing the Rubisco limited. Sorry, it's the other way around. Rubisco limited is this dashed line, and RUBP regeneration is represented by the dash dot dash lines. And we also see there's a thick dark line that is overlapping over here, and that is indicating the minimum of the three values. So if you see this part of the graph, we see that that dark line is going over the Rubisco limited phase because that is the minimum value. Until here, you see that Rubisco limited photosynthetic rate is the limiting factor here because that has got the least of the three photosynthetic rate values. So TPU limited is high, RUBP regeneration limited is also high, Rubisco is the least. But when you come to this part of the curve, we see that Rubisco, the Rubisco values, Rubisco limited photosynthetic rate are higher than the TPU rate and the RUBP regeneration rate, and the least is the RUBP regeneration rate until here. Now, when you come to the third part of the graph, you see that TPU limited rate is the least over here. We see that RUBP regeneration limited rate is higher than TPU limited and Rubisco limited. So, this is how the FvCB model, this is the graphical representation of how the minimum values of the AC, AJ, and AP are to be considered as the A net value. So we three photosynthetic rates will be calculated, and the least of the three will be selected. So if you see at this point, the least is Rubisco limited, and all points the least is Rubisco limited until this part of the curve. From here onwards, RUBP is the RUBP regeneration is the limiting factor, and triose phosphate utilization is the limiting factor in this part of the curve. So this is the significance of the ACI curve. ACI curves can be plotted, and when we do measurements using various instruments that are capable of measuring photosynthetic rate, we are able to get actual plots of ACI curves from which we can understand that uh, which phase is limiting in case of the photosynthesis. Now, the next type of photosynthetic response curve is AQ curve. In AQ curve, we see that the y-axis is net carbon dioxide uptake and x-axis is varying light. If you had seen here, it was intercellular carbon dioxide concentration, but here what you see is it is the varying light. So, light is varying. How will photosynthesis respond to a light variation of 0 micromoles of photons per meter square per second to around 2000 micromoles of photons per meter square per second. So here light intensity is shown in micromoles of photons per meter square per second because light when it comes to plants use light in the form of photons. So the what is the amount of photons responsible for the net photosynthetic rate is what we look at here rather than the general units of light use like watts per meter square or joules per meter square per second only. So in plots of net photosynthetic rate against photosynthetic photon flux density is what we call this quantity is called the light response curves. And in here, just like how we had seen that this ACI curve is giving us this three biochemical limitations of photosynthesis. Here, there are few parameters that we get from the AQ curve that give us insight into how photosynthesis is responding to light. Like there's this light compensation point. If you see here at this photon flux density or this intensity of light, the net photosynthetic rate uptake is equal to the net respiration rate of respiration. So this respiration rate is nothing but the mitochondrial respiration. So mitochondrial respiration, what is the RD value? What is the RD value when what is the light intensity when photosynthesis is equal to the dark respiration? That is, there is no uptake, no net uptake, and net release of carbon dioxide is zero. So information regarding that can be obtained. Then rate of respiration can be obtained. From this curve, we can get that the rate of respiration is around 3 micromoles of carbon dioxide per meter square per second. That is 3 micromoles of carbon dioxide is released out in uh, when you see that leaf. Then there is also after a certain light intensity, the photosynthetic rate neither increases nor decreases. That light intensity is called the light saturation point, and the photosynthetic rate corresponding to that light intensity is called the maximum rate of net photosynthesis. We also get something called the quantum yield. That is, the initial slope of the curve is indicating how efficiently the photosynthesis happens at different at low light. That is, at this range of light where there is a slope. What is the efficiency of photosynthesis? So, if you see, if this is the slope, we get it is less efficient, and if this is the slope, we get it is more efficient. So if you find the slope, that is the change in carbon dioxide by change in light, uh, and depending on that value, we can say how much efficient is photosynthesis happening at low light intensities. The next curve is the temperature response curve. Temperature response curve is the rate of photosynthesis varying with leaf temperature, not air temperature. It is leaf temperature. So generally, we think that when the temperature keeps increasing, the photosynthetic rate keeps increasing, but that is not the case. The photosynthesis will keep increasing until a certain point, after which it starts decreasing at high leaf temperatures. So this is a typical graph that is plotting what is the behavior of C3 plants, C4 and CAM plants at with changing leaf temperature. We see this is how the C3 plants respond when temp with photosynthesis varying with net temperature, and this maximum point of photosynthetic rate uh, at what temperature it is attained is what we call the optimal temperature for photosynthesis. So at this temperature, the rate of photosynthesis will be very high, but as temperature keeps increasing as well as keeps decreasing, the uh, photosynthetic rate is also going to keep decreasing. So high temperature, what happens is it is the decrease in photosynthesis rate is often due to the rubisco deactivation and stomatal closure. And during low temperatures, the limitation is due to enzyme activity constraints. So this is another graph showing the optimum temperature of this obtained from AT curves. We get at what temperature the photosynthetic rate is maximum. From that temperature onwards, as the temperature increases, the photosynthetic rate decreases, and as the temperature decreases, the photosynthetic rate also decreases. So, before I go into more details, so theoretical details, I will be introducing the model BioCro. So, BioCro is a plant growth model that we'll be focusing majorly in this lecture series. Um, BioCro was began in the early, I mean, BioCro was developed in the early 1990s, and that time it was called the VivoMac. In the coming years, crops were added over the years, majorly energy crops like willow, miscanthus, sugarcane, etc. Then after several years, Justin McGrath and a huge team they modified VivoMac into BioCro to reduce the duplicated code and make it more flexible, resulting in the latest version of BioCro. Primary developers of this model are Ed Lochoki, Scott, Dr. Deepak, Megan, Stephen P. Long, Dr. Justice, etc. So you can go through all of these references, which is in chronological order of the development of this model. So BioCro is basically a modular crop growth model. So modular is nothing but when each process, like if you see here, BioCro can simulate photosynthesis, it can simulate transpiration, it can simulate the process called stomatal conductance, it can simulate the process of carbon partitioning. That is during photosynthesis, the carbohydrates that is generated is not just going to stay in the leaf, it is going to be used up by the leaves for growth. So as it grows, how much of carbon dioxide is partitioned into roots, into leaves, into stem. This is what is called carbon partitioning. So BioCro can do that. BioCro can also simulate how the leaves age, and because of that, how much how the carbohydrates partitioning will vary. Then it can also estimate the root absorption, the soil moisture stress, soil evaporation, all of these at leaf scale. Now, when you come to a plant, it is not just happening in one leaf or a bunch of leaf. It is happening over an entire plant that I will be talking about as canopies. For an entire plant, all of these processes are occurring simultaneously, increasing the complexity of simulating these processes. So for that, BioCro also has this multi-layer canopy model where each this whole plant simulation can be done based on how much of light energy is absorbed, or how much of light energy is available to the plants at different heights of the canopy. So based on that, all of these processes will be simulated for the within the entire canopy depending on how much light is absorbed by the plant. So this BioCro framework works like this. I said it's a modular crop growth model. So modularity means nothing but each of the process is simulated as a chunk of code. That is, you can simulate photosynthesis separately. You can simulate the stomatal conductance separately. You can simulate senescence separately. All of these can be done separately. But at the same time, these processes are not separate. So if we have some study of interest that wants us to focus on just the photosynthesis process, then we can do that in using this BioCro. At the same time, say we want to simulate the entire canopy, all these processes are going to be reflected at every layer, every leaf of the canopy. So what we do is we combine the multi-layer model as well as the photosynthesis model to simulate it for the entire plant. Now, say we don't want it for just one time period, we want it for the entire growing season of the plant, we can do that. For that, what we'll do is we'll take all the modules from this BioCro that simulates all the processes, combine it together and simulate it for the entire growing period. So, modularity is nothing but there are a bunch of codes that represent each process. Each of the process will be can be run separately. It can also be combined together to simulate a combined process also. So it is compared to this where we choose the parts from a catalog to make that we want in the car, and we provide the conditions, the specifications, send it to factory and produce a car. Same, we can choose equations or modules from the library that represent each process. Then we can provide what are the parameter values and the initial values and whatever input data is required for all these modules and send it and run BioCro to obtain the result. So BioCro is a semi-mechanistic process-based model. It is a generic model, that is, it can be used to simulate any kind of terrestrial crops. As of now, certain bioenergy crops and soybean is can be simulated using BioCro. Eventually, we can develop it or we can parameterize it for any kind of terrestrial crop, and it can do simulations at the leaf scale that can be scaled to the canopy scale and field scale as well. Now, BioCro soil module is a very simple module. It is making use of a bucket model that makes use of water balance method to represent the soil water and soil water content. So, BioCro's advantage is majorly its modularity, and also we can run this BioCro model using R, which is comparatively user friendly than many of the programming languages. And then it is also developed in such a way that, say, tomorrow we don't want to run it in R, we want to run it in Python. Then there is a Python to C file conversion possible. So the coding has been done in such a way that if tomorrow if you want to run it in Python or R or any other language, there are codes which will help in converting the whatever base files into the appropriate language that you require. So let us go into the modeling part of BioCro. So if you see here, initially when you in order to install BioCro, you can use this line install.packages BioCro, which is the standard command to install any package in R. So when you run this, BioCro is available as an R package. It will automatically get installed within your local system. So I have already installed BioCro, but again for the sake of understanding, I'm just doing it again. Now apart from this, you can also go to Tools, Install Packages, and then you can type in BioCro and install it from here also. Now in order to load any package, you are supposed to type in the command library and then the package name. So if you see here, library, I type in BioCro. Since BioCro has already been installed here, when I select this, we see that this library is has been chosen. Library where BioCro is installed has been chosen, and when I run this command, the library will be loaded. Next step is to understand what all functions or what all processes are there in BioCro that we can simulate. So once we load the library, if you type in the command get all modules. So here the get all modules function will help us in obtaining whatever modules are available in BioCro available for us to run. So when you put in this function and type in BioCro, if you see the console over here, console is whatever the output of whatever you run on this, you will find whatever So when you open an R file, whatever you run on the lines that you run, the outputs will come in this console. So when I ran this get all modules BioCro, these are the processes that BioCro can simulate. It can simulate the ABA decay, Ball-Berry equation, biomass, the limitation due to nitrogen. Then there is a soil drainage module, C3 assimilation module, C3 canopy module, C3 leaf photosynthesis module, C3 parameters. Similarly, for C4 also there are some functions available. For canopy, there are some functions available. There are, if you see, the FvCB equation is available that we just studied. Leaf evapotranspiration, and so many more processes are available in BioCro to be simulated. So I had just explained to you about the FvCB equations. So I'm going to run the FvCB module, that is one that simulates estimates the FvCB equation. So in order to do that, first I don't know what are the inputs and outputs required for BioCro for the FvCB module. So I'll just use this command, module info. Now module info is also a function in BioCro, just like get all modules. I'll type in module info, which is the module that I want to. So if you see here, all the modules in BioCro are represented by BioCro colon and the module name. You can't just write the module name as it is. You have to write it in this format, that is BioCro colon whatever is the module name. So I want to run FvCB model. So I'm just going to directly copy paste this line, that is BioCro FvCB, into here, or once you're familiar with the software, you can just um, write the line down. So if I put module info function and put this argument over here and run this line, we will see that we get the information regarding the module. So the name of the module is FvCB. The input quantities required is CI. CI is the intercellular carbon dioxide concentration that I had talked about earlier. I can show it to you here. Yeah. So Ci over here is the intercellular carbon dioxide concentration. G star is nothing but the carbon dioxide condensation point. J is coming in the RUBP limited photosynthesis, this value, which is rate of electron transport. Kc is again coming in the Rubisco. Kc, it is a Michaelis-Menten constant for carbon dioxide. K naught is the Michaelis-Menten constant for oxygen. OI is the oxygen concentration inside the cell. RD is nothing but the dark respiration rate. VC max is this parameter, maximum carboxylation rate of Rubisco. Alpha TPU is a parameter in the TPU limited photosynthesis, but in this model we are using a value of 0, which will result in obtaining this final equation. So alpha TPU comes in the TPU limited photosynthesis as a term like minus and a numerator and denominator, but because alpha TPU is equal to 0, the final equation will be reduced to this. Then electrons per carboxylation is nothing but this EC minus, and electrons per oxygenation is EO minus. So if you see all these three equations, we are sorry TP yeah we have the AC equations parameters VC max, EI, tau, KC, O, K naught. We have J, CI, tau star, and the carbon dioxide. EC we have, CI we have, E naught we have. We also have VTPU, that is this value, the maximum rate of triose phosphate utilization. So these are the input quantities required for estimating. So we have all the RHS values and we will get the LHS values, which are AC, AJ and AP. Now FvCB equation gives the takes the minimum out of AC, AJ, AP and then subtracts RD value from it. So now if you see here, the output quantities are AN, AC, AJ, AP. That is, AC will be calculated, AJ will be calculated, AP will be calculated, and from this three values, whichever is minimum is what is going to come as the AN value. Now, if you see here, there are certain other other output quantities also generated. It is nothing but in the FvCB equation you see here, we see here this Ci minus tau star is taken as Vc because it is common in these two equations. We consider the Ci minus tau star as common, and that is what is called as Vc in this output quantity. And Wc, Wj, Wp is nothing but whatever comes outside this Ci minus tau, that is Vc max by Ci plus Kc, this Vc max by this denominator and J by this denominator is what is the Wj and Wc. So that is about the input quantities and the output quantities. Now let's see how we can run this model. So in order to run this BioCro model, I mean module, I'm not talking about the entire BioCro model, I'm talking about this module which is called the FvCB model. We need these input quantities and we need these output quantities. So what function do we use to run a module? And running FvCB module is done using the function evaluate module. So for evaluate module function, if you go in here and if you don't know what arguments are required in this evaluate module function, we just put a question mark and we put in the module function that we require to run. So when you run this, in the right hand side you will find that there are module info function that is returning essential information about a BioCro module. There is evaluate module that runs a BioCro module using a list of input quantity values. So what input quantity values are required by module info is given here. Module evaluate module, the arguments required are the module name and the input quantities. So if you see, when we use this function module info, the argument required is a module name. So that is why we gave module info and the module name in this format. Similarly, in evaluate module, we require the name of the module similar to module info as well as the input quantity. So two arguments are there for using this evaluate module. So what we will do is first we will prepare the input quantities that is required for this evaluate module function. So input quantities that is required for the FvCB module are, like we had seen, G star, J, Kc, K naught, OI, RD, TPU, Vc max, alpha TPU, electrons per carboxylation, electrons per oxygenation. So these are the input quantities that we require for running the evaluate module. Now, once again, to refresh, what are these quantities? This is intercellular carbon dioxide concentration in micromoles per of carbon dioxide per meter square per second. G star is the carbon dioxide condensation point, also the same unit of Ci. J is the maximum the rate of electron transport, not maximum, which is in micromoles of electrons per meter square per second. Kc is Michaelis-Menten constant. K naught is Michaelis-Menten constant. OI is the oxygen concentration inside the leaf. RD is the dark respiration rate. TPU is the maximum rate of triose phosphate utilization. Vc max is the maximum rate of Rubisco carboxylation. Alpha TPU will be 0, which is a term that is related to TPU limited photosynthesis. Electrons per carboxylation is the amount of electrons required, number of electrons required for carboxylation reaction, and amount of electrons required for oxygenation reaction. So these are the input quantities. Now I have put a sample set of input quantities. So let's first run this list. So when you run this list, we get the parameters. Once you run this one, we get parameters over here, a list of parameters, which is Ci, G star, J, whatever we gave in. So it appears as a list over here. Now next what we'll do is, we have all the input values, and the we will use this evaluate module function to run this FvCB module. So in evaluate module function, we require to put the module name and the input quantities as well. So we have put the evaluate module name and input quantities, and when we run this module, we will see that we have got a list of outputs. So initially, when I was explaining the model output quantities, AN is the net photosynthetic rate, Rubisco carboxylation limited photosynthetic rate, AJ is the RUBP regeneration limited photosynthetic rate, triose phosphate utilization limited photosynthetic rate. VC is a term that is separated out from the equation so that it is easy for simulation, and WC is the remaining of the term after which VC has been separated. So this combination of these two will give AC, combination of WJ and VC will give AJ, and combination of WP and VC will give AP. So once we run this module using the function evaluate module, we are getting that the value of AC is 21.6, value of AJ is 14.3, and a value of AP is 2290. So because of that, AN value that will be selected is the minimum of these three values, minimum of this value, and this value. So the minimum of all these three values is AJ. So that is why AN is equal to AJ. Okay, so this is how we run evaluate module, or we run a particular module for a set of points. Now I had also explained what these response curves are. So I did say that for this ACI curve, we can get which at which value of photosynthetic or intercellular carbon dioxide concentration is the Rubisco a limiting factor, RUBP a limiting factor, and TPU a limiting factor. So next what we are going to do is how do we plot all of these ACI curves. So in order to plot curves, there is another function called module response curve. So just like how we looked into the evaluate module, let us also look into the module response curve. And when you go to the help section, you will find that module response curve is a function that requires the module name, the fixed quantities, and the varying quantities. So if you look at the photosynthetic response curve, carbon dioxide response curve, we see that we are finding out the assimilation rate for varying values of intercellular carbon dioxide concentration. So in order to do that over here, we use this module response curve function, give the module name that we are which is the module or the equation that we are using to generate the curve, what are the input quantities that are fixed, what are the input quantities that are varied. Now from running the module info, we know that these are the input quantities required by the module FvCB. And from all these input quantities, we also know that Ci is the one in the x-axis which is going to vary. So fixed quantities will be all these G star, J, K, C, K naught and all of that, and varying quantities will be Ci. So in order to define the fixed quantities, we will name a list of all these input quantities called fixed and put in all the same values of G star, J, Kc, K naught, Oi, Rd, Tpu, Vc max, alpha Tpu, all of that will be constant, but the one which is varying is the Ci value. So we'll define a variable in the or sorry, we define a data frame that will comprise of this varying quantities. So when you run this fixed list, we see that the fixed parameters which are all fixed is available. And next, when we run the varying quantities data frame, we see that we have a data frame of varying quantities, that is Ci is going to vary from 150 till 1500. So all the assimilation rate corresponding to this 150 Ci, 200 Ci, 250 Ci, 300 Ci will be simulated over here. So now we have run the fixed quantities, we have defined the fixed quantities and varying quantities. We will name a variable that will store the results of this by results of running this function. So like the help document has explained over here, the module response curve requires a module name, which we have given here, comma, the fixed quantities, which is the fixed list of fixed quantities that we have defined here, and varying quantities, which is the data frame of CI values that uh, we have defined here. So using all these three arguments, we are going to run this function called a module response curve and storing it in another variable called ACI. So if you look at the ACI that has been generated after I run, it is a data frame where you get for each CI value, they estimate what is the G star, J, K, C, K. All these values are constant. So we put in all these CI value, which is the only varying value over here. You see, CI is the only varying, but G star, J, KC, K naught, OI, RD, TPU, VC max, alpha TPU, electrons per carboxylation, electrons per oxygenation. All of these are constant, and for each of these constant values and the changing CI value, what is the Rubisco carboxylation limited, what is the RUBP regeneration limited, what is the TPU limited, and what is the net photosynthetic rate is estimated. So this is the tabular format of the results. But what we want to do is we want to see how the ACI curves looks like. So in order to plot any curve, there is a library called the lattice available in R, and so I will run this library and using a function called xy plot. Again, if you don't know what are the arguments required in xy plot, you can put a question mark and then get the help for xy plot. And here they are saying that, oh, xy plot requires the data, I mean the x-axis and data. So here also you can see how an examples of how xy plot is done. And they'll also have, I think, a base simple example below in this help document that will help us in. See, if you see XY plot, they are plotting latitude and longitude. So latitude is the y-axis value and longitude is the x-axis value. Similarly, over here we want some length and width in the y-axis vary and to see what is its value differing with the x-axis. So in here what we want is we want to see what is the rate of AC, AJ, AP in x-axis and estimate and see which is the least carbon dioxide least value that is coming. So for that I ran this library lattice and then using this function I am plotting this curve. So if you see the curve over here, you can see that AC, that is the Rubisco limited photosynthetic, is depicted by this blue line. AJ, which is the RUPP regeneration limited photosynthetic rate, is depicted by this yellow line, and AP, which is the TPU limited photosynthetic rate, is depicted by this green line. So if you compare it with the standard curve that I had shown in the PPT, this dashed lines is what is this AC value. This dash dot dash lines is the AJ value, and the straight line is the TPU limited photosynthetic rate. Now we very evidently know that a minimum of these three values is this AJ. So this entire photosynthesis in this plant or in this leaf is limited by RUVP regeneration. That is, it is mostly affected by the rate of electron transport. So the A net value, if you look at this now, if I plot A net also along with this and run it, you can see that A net is given by this dark orange line, and that orange line is overlapping over AJ value because that is the most minimum value. Now let us see how the plot will vary when we change certain quantities. So we are going to change a J value, say to 200, J value, rate of electron transport, to 200, and we are going to change this value to, no, let us keep the value Vc max as it is and Tp also as it is. Now let's see how this curve will vary. Now we see that TPU is as usual very high. TPU is very high. AC, which is the blue line, initially it was more than the AJ. So until this point of the CI value, until this CI value, the minimum photosynthesis is contributed by Rubisco limited photosynthetic rate. So here we say that the photosynthesis is limited by Rubisco carboxylation. After this point, again AJ is the limited photosynthetic limiting factor. So after this point, we say that the RUVP regeneration is the limiting factor in this photosynthetic rate. Now, if you plot AN also along with this, you can see AN is represented by this dark orange line, and you can see over here how this blue value of RUBP is overlapped by AN value, and after this point you see all of the photosynthetic net photosynthetic rate is contributed by the RUBP regeneration limited. So again, if we increase the value of J into say 300, you will see that again over here we are seeing that AC is the limiting factor until this CI, intercellular carbon dioxide concentration. After that AJ becomes the limiting factor. So this is how we can use ACI curves to understand the biochemical limitations and what is majorly affecting the net photosynthetic rate.